All right, I'm going to quickly redraw the problem, and then we'll work on it. This is 27, right?
Mm-hmm.
In fact, I think I'll just go ahead and draw it and break it up into the three free bodies I think that would be best suited. So there is a free body, which means you could draw the first one. We'll call that AD. It's 3 meters. And the fixed connection at A, I'm just going to assume that I have a reaction AY, AX, and a moment. And I assumed all those directions, like I normally do, just positive. X is to the right, typical of an x-axis. Y is up. And then I use, for most of my moments, I always use the right-hand rule. So I'm not even thinking about what they're going to be. Then at point D, which is a pin, and the great thing about taking a structure apart at a pin is that there is no moment. So there's just going to be two unknown forces. So again, I'm just going to assume that I have something called dy and something called dx. So I'm just making an assumption about that. In addition to that, I have it's going to be hard to draw on there now, but I really have a load applied. Let me kind of hang it off the bottom here. There's a load there of 8 kilonewtons. Okay, I'll just call this free body 1. Now I'll do free body 2, where I'll start with the next section, so it'll go from pin D to pin B, and that there's a 6 kilonewton force on that. Actually, the dimensions are 2 meters and 1 meter. Now, since I've already assumed directions for dx and dy, they're what on this other free body? Equal and opposite. So I don't get any choice there. If you make a mistake and make some new choice, you're doomed to failure. It sounds a little extreme. And the great thing about here, too, is if you add these two bodies back together, what happens? Automatically, dx cancels each other and the dy cancels each other. Now I'm over to B, and now I'm going to assume, again, something at B. So I'll assume that dy is up and bx is to the right. Now I should also mention that if you look at free body 1, how many unknowns do you have? 3 plus 2, you got 5. How many equations of equilibrium do you get with one coplanar system? 3. So this is not a good place to start. Right? Now the middle one looks a little bit better. We have 2 and 2, so that's 4. We might be able to do something there. Let's go ahead and finish it and go all the way out to the third free body, which would be the very end, from B, E, and C. So we've got a reaction at E. It's a rocker. So that would be EY. And then all the way out at C, we have another one. And the dimension, and then there's a force right here in the middle of 12 kilonewtons. And it's something like 1 meter, 1 meter, 1 meter. Again, I've already assumed directions for bx and by, so in this they are, again, equal and opposite. So for me, that's the problem. If you can break it apart and visualize these three free bodies correctly, then it's just a matter of applying your equations and deciding where to start.
I got a question.
Yeah.
Why can you not separate BE and EC?
B where? Where do you want to cut it?
BE and EC. When I did it, I separated everything.
Well, if you make any cut in any of these bodies except at those pins, you're going to generate 3 unknowns. X, Y, and a moment. So you're not going to help yourself, because as you take it apart, now you have two bodies. You generate another set of 3 equations, but you just generated 3 more unknowns. So you haven't helped yourself. The great thing about taking them apart here is I get 3 more equations, but only 2 unknowns. And when I take it apart here, I get 3 more equations, but only 2 unknowns. So now I have 1, 2, 3 equations. 3 bodies, which will give me 9 equations. Now, there's some pretty easy things to start with. I would actually start with number 2. If you look at number 2, there's a couple different ways to do it. If you sum moments, I'll use positive as my sign convention. Let's say I sum moments at D and make sure it's in equilibrium. What do I have? Well, I have this 6 and I have BY. So I can find BY. I'm not going to go through the details right now, but from that you should be able to what? Find BY. Right? Now what do I do? On the same free body, I can sum forces in the Y direction. And what will that give me? dy. You say, what about the X forces? Well, they may not even be a problem right now. In fact, they won't. Now I can do what? Now that I know these, I can go any way I want. Let's go to number 3. Since I know BY, can I find EY or CY? Sure. So again, sum moments. You can pick either E or C. I'll just pick C. So when I sum moments about C, what am I going to get? Well, the only unknown is EY. And then again, I can sum forces in the Y direction, and that should give me CY. And while I'm there, why not sum forces in the X direction? And what is that going to tell me? What BX is. And that's the easiest one. It's 0. Well, then I can put BX onto this one. Sum forces in the X direction. That tells me DX is 0. So I can finally pile it all back over here. I know DX is 0. I found DY. You can sum forces, sum moments, and find the reactions. Just work your way across.
If all of your loads are vertical or acting perpendicular to the beam, do you really have to worry about the X?
Well, you should never worry about anything. That's my advice to you. But when working this problem, I think it's easy to communicate to me that you understand that the sum of the forces in the X direction is 0, and that you take the extra 2 seconds to write down sum of the forces X equals 0 and BX is 0. Then I know exactly what you're thinking. There's no guessing. You don't want me to guess when I'm evaluating your work. Right? You want to tell me what it is you're thinking.
So when you break apart these beams, all of the BX's or DX's in this case are going to meet together. Always. Whenever you break up any type of beam. It's always going to be pulling away from the center.
I don't know if your explanation is correct. I think it's better to think about it that when you take this thing apart at a pen is special. A pen has no moment. Right? But it can still provide forces in the X and Y direction. So if I started like I did here with the first side and I assumed direction for dx and dy, okay, fine. But they have to be equal and opposite on the other piece.
Okay.
So when I take free body 2 and add it to free body 1, what happens here?
They go away.
They go away. Because there is no external force there.
Okay.
You can't add them together and get something extra. Because when you look at the problem as posed, there's no force at pin D. Now there is, there is this force here that we will account for. And it will make an effect on D. But you know what? We don't care about D. What do we care about? The reactions. What happens at A E, and C. This other stuff is just things we need along the way to make it work. Now, if you mess those up, obviously you're going to mess up the reactions too. This is on the limit of a problem that would be acceptable on the exam. So it's a little bit. It's a lot of work. I think conceptually, this is the most important part. If I were to grade this problem, say out of 100, I'd give you 65% for drawing these free bodies correctly. That's not passing, by the way, but it's pretty close. I view this part of it as just mechanics. Right? You could almost train a machine to do that. You don't need to think too much to do this. This is the thinking. You're taking the problem and breaking it down into something that can be analyzed with the tools that you have. At this point, you're just applying the tools. Now, I still want you to do well, and obviously you would lose 35 points if you didn't process the numbers right. But I see the free body and the setup of the problem usually about 2/3 of the effort. Now, that won't help you on the FE or any kind of multiple choice test where the answer is the only thing that counts. But in this course, I still am interested in what you're thinking, and this is how you're going to communicate that with me. Free body diagrams.
Excuse me, I got a question.
Yeah.
What about the 10 kilonewton force? We used it only in the first rolling diagram.
Well, it's unknown. Whenever you have a force acting at a point like that, you can assume it's either at the edge on one side, at the edge on the other side, or any combination. You could actually say 4 of it's here and 4. It won't matter, because when you start summing forces, dy is going to compensate for that. It won't matter.
But we don't put like 8 kilonewton on both.
No, you can't put it on both because there's only 8 kilonewtons. So if you put it on both, you now have 16 kilonewtons. Right? Because when you put these back together, dy cancels and there's your 8 kilonewtons. If you add it on both sides, suddenly you add them together, you get 16. So you got to put it on one or the other. Or share it or something.
If we had done it like you did dy, and we did, there was 8 kilonewtons going down, and on the opposite side put 8 kilonewtons going up, and it canceled, would that work?
No. Now you have no force acting at the node. When it all gets assembled back, basically all the stuff I did in blue disappears, right? And all you're left with is the stuff that's in black. So if you have 8, I better do it over here because I can't see it. If you have 8 kilonewtons here, you can't have 8 here. When you put them back together, you get 16. If you put 8 down here and 8 up here, you put them back together, you get nothing. Different problem.
So it doesn't matter which one you put it on.
No. Because if you put it on this side, it's going to affect dy, and dy will show up over here, and it'll give the same effect into the moment and the reactions here. Yeah.
When you're on free body number 2 and you do some of the forces, you find dy, and then you get down to in the problem when you're on free body 1.
Right.
Since dy is countering the 8 kilonewtons, let's say it's like.
It's not countering, it's bringing the effect of this free body onto this system.
Can you simplify your free body by just doing, let's say dy is 2 kilonewtons. Can you just say you only have a downward force of 6 kilonewtons going down?
Well, yeah, if you have two forces at one point, you can get the aggregate of them. That would work. But sometimes, my experience has shown me that it's best for you as a student under the pressure of an exam not to confuse yourself. And I think you just take the simple short path, which is don't worry about it. If you wrote dy here, then just treat it as dy. Don't get in the middle of the exam and say, oh, dy is up of 3 and I got a down of 8, so that means I have a down of 5 or is it up of 2. Or just don't even worry about it. It's two forces. dy is up, creating positive moment. 8 kips is down, creating negative moment. Just add them up that way. Let the equation take care of it. Let the mechanics of the equations do the work. You just set it up. You do the thinking, let the equations do the work. And by the way, this kind of stuff is going to be throughout we're going to have this all the way through the course. You're never going to stop doing this until you leave this course. All right? And then you're going to take steel design or concrete design. You know what the first thing you're going to do? You're going to do this again. Now, this is pretty fundamental stuff, finding reactions. And what we're going to do as a little preview is we're going to worry about forces inside a free body diagram, the X, Y, and moment force, and as they vary. And we're going to learn techniques to write equations, to draw diagrams, and that's the basic fundamental characteristic of a beam or a column that you use in design. When you design a beam, you want to withstand a certain moment, to withstand certain forces, whether it's concrete or steel. Actually, concrete is a little more, I think, complicated is not the right word, more detailed in how it handles those things. Okay, any other questions?
Are you going to